Hello everyone! Today I'm going to show you how easy it is to run training of large-scale transformer-style models on a single CS2 system. We will be training a model with 1.3 billion parameters, which is still large enough, and even larger model with 6.7 billion parameters. And what's nice, I will show you that you can do that with exactly the same code base without worrying about how to distribute the training across multiple devices. It all runs on a single system, and you write the code like you would write it on for a single device. So let's get going. I will be leveraging our Python implementation of these transformer models. We have those implementations also available. You can take a look at these at Cerebras reference implementation GitHub. Here I have a clone of the repo, of the models repo, and I have implementations of those GPT models. So this is standard Python code relying on TensorFlow. I have different Python scripts, definition of the model, my training script called runpy, a bunch of utility scripts. In order for us to make it easier to experiment with different model configurations, we put all of the main model configurations into separate YAML parameter files. So for me, in order to change the configuration of the model from this 1.3 to 6 billion or even to 13 billion or 20 billion parameter model, all I need to do is to change the definition of the model in a YAML config. So let's take a look at how those configs look like. Today, I have prepared two configuration files, and we will go through those in detail. So one of them is again for 1.3 billion parameter model called GPT-3 XL, which is defined to be trained on pile dataset. And the second is a larger model with 6.7 billion parameter models. So let's take a look at one of those definition files. In this file, we define the main model parameters. So we define things like their size of the model in terms of the hidden size. We define the depths in terms of the number of hidden layers. We define number of attention heads. We specify also which optimizer we would like to use and different parameters for this optimizer. And here I also configure things like how frequently I would like to log the run, so how frequently I would like to see the losses, how frequently I would like to store checkpoints, and how many checkpoints I would like to store, and for how long I would like to train that model. So all of their information which a typical ML researcher cares about, most of it can be configured from this file. So with this, now let's take a look what it looks like to run a training job on a Cerebras system. In order for us to allocate resources on the Cerebras system and on adjacent CPU nodes, which are used to run compilation and to stream training data to Cerebras system, we are using a standard orchestrator Slurm. And for me to run a job, I will be using a wrapper around Slurm, which loads Cerebras environment onto the CPU nodes, allocates all the resources, and launches the training. So the name of this Slurm wrapper is CS-run WSE. So I will be running that. And then I will telling this Slurm wrapper what application I would like to run. So I will be running Python, and I will be passing to Python our training script. Now my training script gets as an input several command line arguments. One of them is a mode. So I'm running train job, so I would like to tell them that I would like to train a model as opposed to running inference with that model. I also would like to specify where to store the outputs of the training, where checkpoints will be stored, where their TF events will be stored, which then I can hook up to the tensor board and monitor my run. So let's name it something which will tell us which model at training. So I'll choose this name. And then I will pass parameters. So the YAML file, which we just took a look at. And next, I will also pass CS IP address, which I stored in an environment variable prior to the run. And for this demo, I will be running a shorter training job, so I will be running just for 2,000 steps. So let's get going. Once I launch the training, what happens behind the scene is that our Slurm wrapper is asking for allocating some resources, and then we get resources allocated. and then the compilation starts. So we extract the compute graph from the TensorFlow and then compile that into an executable which can be loaded on the wafer scale engine. So at this point, we are at this point of compilation, we are waiting for a compilation to be completed and for the compiled artifacts to be created and passed towards the wafer scale engine. It will take a little bit of time. So now the compilation is completed. So you see we compiled everything through XLA, and we are waiting for the first losses to be streamed out of wafer scale engine and to appear here in our std out. So at this point, I will just expect a normal output of a TensorFlow run, which will tell me the loss and the rate. Here we go. So the first 50 steps are processed. We are going with the rate of roughly 0.5 steps per second. So as you can imagine, running for 2,000 steps, it will take a little bit. So we'll come back when we are done through this. The run for 2,000 steps has been completed. You can see here on the screen, I have all the losses printed out, and it looks like we did the training with a more or less stable speed, going roughly half a step per second. So let's take a look now at the training artifacts. Let's take a look what's in the directories here. So now we can see some compile artifacts, and we also have this GPT-3 XL pile folder. So that's the folder with the checkpoints. That's the folder with the all outputs of my run. So here you can see that I have checkpoints saved at the end of the training. I run for 2,000 steps, so I have a checkpoint at 2,000 steps. I also have a standard TF events file, which now can be used to look at the tensor board at the progress of the training. So let's do that. So we see our loss curve for 2,000 steps, all going down and nice. So again, during the longer training run, you can hook tensor board during the training process, and you can monitor the progress of the training using familiar tools like a tensor board. That was an example how you would train a 1.3 billion parameter model. Now, before I show you how to train a 6.7 billion parameter model on CS2, let's do a little of detour and think through what it would take you to do that on a GPU. In order to train large-scale models on clusters of GPUs, you have to rely on a multitude of distribution strategies. So for a model as big as 6 billion parameters and above, you typically can't feed that model into a memory of your GPU device, and you're forced to rely not only on a most simple way of distribution, such as data parallel, but you also rely on pipeline model parallel and tensor model parallel distribution. As a matter of fact, in the literature, people call that 3D parallelism or hybrid parallelism. And every time when you train a new model, you have to specify, as a ML researcher, you have to decide what's the right way to split your model, how to distribute that model across several devices. Obviously, the simplest way is with data parallel training, but you can do that only if your model fits into a single device. That's not the case with 6 billion parameter model. So you will have to go through either tensor model parallel when you split every single layer into several devices, or with pipeline model parallel training when you decide which layers belong to which devices. And in most cases, you will have to use all of those schemes. We did a little bit of study and took a look what types of parallelism are used or has been used historically to train large-scale GPT-style models. So on this a little bit complicated plot, what we attempted to show is how people trained models from few hundred millions of parameters, like Megatron with 345 million parameters right here, and all the way up to a trillion parameter model across large-scale clusters of GPUs. Color breakdown here tells us how many nodes have been used to leverage a certain parallelism. So gray here stands for data parallel training, so that means that you will rely only on data parallel training, and the number of nodes which has been used to distribute in a data parallel fashion is a logarithmic scale on the left. So here 2 means that I would use 2, here 8, and 16 devices. As you can see, for smaller models up to 1.2 billion parameters which can fit into a memory of a single GPU, people use the simplest way. they just rely on data parallel training because it's really easy to get that going, especially when you're training on a single box. But then as you start to increase the size of the model, you no longer can rely on data parallel training alone. And you need to bring into the mix model parallel training as well. And then it becomes an art of optimization to understand across how many nodes you would like to distribute using data parallel training, across how many nodes or GPUs you would like to distribute using model parallel training, and different flavors of model parallelism. So as you can see, the next area of parallelism to add into the training is tensor parallel. So when you split every single layer into multiple devices. So you will rely on that. Now you can fit larger models into a box by dividing the model using this tensor parallel training. One caveat though, that typically when you train on GPUs, people don't use tensor parallel training across multiple boxes. So usually the number of devices which you can use and leverage with this tensor parallel training is only limited by a single box. And that's why this kind of dark blue part across all of the options is not that big. So people typically limited by their bandwidth and latency within a single system. And tensor parallel training requires high bandwidth and very low latency to be efficient. So you don't want to break it down across multiple systems. Then at some point, when you need more systems that you can distribute with just data parallel and with this tensor parallel training, a third parallelism comes into play. So now we also rely on pipeline parallel. And as we grow the size of the model and as we typically grow the size of the cluster which will be used to train those models, we increase this pipeline parallel thing. Again, as I said, this is just an example how people train those models. It's not trivial to decide what's the best way to split the model across multiple devices. It could be that you can get high performance even leveraging model parallel on smaller models. It could be that some of those options here are also not optimal. It highly depends on the structure of the model, and it highly depends on the infrastructure that you have. Connectivity between systems, connectivity between GPUs. So every single design have to take into account both properties of the model and properties of your cluster, which is really hard to understand what's the optimal way to run that. One other point which I would like to make is using also different types of parallelism impacts on which batch size you're capable to use. So here on the right-hand side, I also have numbers for a batch size in tokens, which has been used for all of those runs. So this purple line or magenta line is the actual batch size which has been used for those runs. And below green line is the critical batch size or most optimal batch size that you would like to use by training when training those models according to the scaling laws to get the most efficient training. And you can see that in most cases, the actual batch size that have been used is above. So it's higher than the optimal batch size. What it means that likely to train to the same accuracy all of those models, you could achieve in a less number of epochs if you can afford to use a smaller batch. But unfortunately, all of those parallelization schemes, especially data parallel and pipeline parallel, they require you to run with larger batch. So they push the batch size up in order to be able to utilize the infrastructure. So that's all how you would run those large-scale models on clusters of GPUs. And the model which we will be training right now, 6 billion parameter model, which we'll be training on a single CS2 device, belongs somewhere between here. So it's the model which you won't be able to train relying on data parallel training only. You will have to rely either on tensor parallel or pipeline parallel on top of that. And again, it's not completely obvious how to break this down into multiple GPUs. So now let's take a look what it looked like to train the 6 billion parameter model on a CS2 system. We've been running a training job with a smaller model. Now let's run exactly the same, a very similar training job, but with a larger model. Before we do this, I just want to show you the difference in configuration files between those two models. So I'm comparing the parameters which have been chosen to train this GPT-3 XL model with parameters that I will be using to train a 6 billion parameter model. So you can see there are only a few lines which are different, and these lines are exactly the lines which define the model. So I'm increasing my hidden size from 2K to 4K. I'm increasing the depth of the model from 24 to 32. I'm increasing the number of attention heads. I'm increasing the size of feed-forward layer. And I also set a higher frequency of logging, because a 6 billion parameter model takes longer to train. So for me, in order to see some feedback from the system, I would like it to send me losses more frequently. It's just a convenience. So these are the only changes I'm doing. I don't change the code. I don't change anything. So I'm running exactly the same command as I ran before. So we've only changed 5 parameters. And now we are running exactly the same command as we ran before. So I'm running exactly the same training script. I also would like to run training. Now I would like to create a new output directory. I will call it GPT-3 6.7 billion train on pile. I will pass a different configuration file. So this time I will be using this 6.7 billion parameter file. I still need to pass IP address of the system, like I did before. And this time I will train just for thousands of steps. So as before, we are queued and waiting for resources to be allocating. We're going through exactly the same process of compilation. It will take a little bit longer this time to generate the first checkpoint and to copy it into CS system. So the model has been completed, and we even went through significant amount of training already. So we see that a number of losses has been already printed, so the model is still going on. But you can see that the training run is going on. It looks exactly like it looked like when we trained a smaller model, except that we have right now a slightly slower rate, so we're processing at a slow rate because the model is so much bigger. But like before, we can now check also the outputs of the training, and we can also look at the tensor board and check where the run is. So let's do that. Okay, we're actually almost done for 1,000 steps, close to the end. So you can see that the model also converging, everything is going fine. So our 6.7 billion parameter model is training on a single CS2 device, and everything looks good. So you've seen for yourself how easy it is to train large-scale transformer models. Let me show you once again how we switched from 1.3 billion parameter model training to 6.7 billion parameter model training. On this slide, I show on the right-hand side a table which is taken from the original OpenAI paper on GPT-3 model. It lists all the configurations of that model that OpenAI team has tested, including 1.3 and 6.7 billion parameter models that we've started training today. On the left-hand side, I show the YAML config file, which we've looked at and which we changed today in order to switch from 1.3 to 6.7 billion parameter model. So the only things which you need to change to go from 1.3 to 6.7 billion parameter model is this. So you change the size of the model, you change the depth of the model, you change the number of attention heads, and in our implementation, we also ask to change the size of feed-forward layer, which is typically 4 times larger than the hidden size. That's it. As an ML researcher, you can do other changes if you wish, but you're not forced to. We've seen model converging in both of those configurations. It all runs with a single code base. No changes to the Python code has been made, just the YAML configurations. In contrast, if you are to switch from 1.3 billion parameter model to 6.7 billion parameter model on the GPUs, the same code base is unlikely to work. If you rely on some complicated libraries, you will still have to manually decide how to split the training of these larger 6 billion parameter models across multiple GPUs. It will be on you, on ML researcher, to decide how many GPUs you would like to use for data parallel, how many GPUs you would like to use for model parallel, which flavor of model parallel training you would like to use. And depending on the model configuration, you will have to change that recipe. Every time you change the ratio of depth, width, every time you change the model slightly. So it's a very brittle, and it depends on model configuration, and it depends on your infrastructure. So the decision how to spread it will also depend, let's say, how many GPUs you will have on a single system. So all of that is really custom again to the model configuration and really custom to the cluster. And in contrast on Cerebras, because we're running all of those jobs on a single CS2 system, we don't need to take care of that. Our compiler decides what's the most optimal way to distribute all of the computations across hundreds of thousands of cores, which you have on the single wafer scale engine. So you run your code on wafer scale engine on a CS2 system, like on a single device, because you are running on a single device. It makes your life so much easier as an ML researcher, and it gives you an opportunity to easily switch between different model sizes. So I've shown you how to switch between different configurations of GPT-3 model. Just as a teaser, we also have an implementation of GPT-J model. Actually, I have it right here. And I even attempted some runs already. You can see some of the log files. So for me, in order to switch between GPT-J model configuration, if I would like to train 6 billion parameter model, or maybe if I would like to go with the new OX version, which is 20 billion parameter model, again, the only changes I will need to do is to change the definition of the model in a similar config file like we've done for GPT model. So here for our GPT-J config file, you can see same model definition. So this is definition for 6 billion parameter model. If I want to switch to 20 billion one, I will have to change the depth of the model, the size of the model, to make it fit their published configuration. And if I would like to train a model which is in between, I can also do that, and I don't need to think about how to distribute that across multiple devices. I can run that on a single CS2 system. So you've seen by now that it's really easy to train those large-scale NLP models. If you believe that that can help your business, and there are a lot of applications where those large language models can be really helpful, please contact us, get in touch. We will be happy to help you and to get you going with the training of those large-scale models on a single CS2 system without you needing to think how to distribute your computations across clusters of multiple GPUs. Thank you.